because you have enough material that it won't seem overwhelming. It's a good point to really focus and gather all that information, do a little cramming. Make sure you're clear about all that stuff before we move on. Now, if I wait too long, what happens is, then you have waveguides, optical fiber, propagation and free space, and then you have propagation and conductors, oblique incidence, and you're going to have 20 or 30 different topics that you can easily garble. Here you're going to have a finite, I think it's a manageable amount. Follow me on this class. Before we get into the harder stuff, microwave and things like this, I want to deal with this. So now I want you to think about a test date. You're going to vote on it. This we'll be done with chapter 8 in about another 2.5 lecture periods, roughly, okay? We'll be finished with the stuff out of chapter 8, but that's an estimate now. So think about in the next 2 to 3 weeks when you'd like a test, and then how about next time on Monday? Can you remind me, Tyler, that we're going to vote on it? You too, all right? And we'll just vote on the test date. You fair? Everybody good with that? So show up Monday if you want to vote, and if you don't show up, you don't get a vote. That's my thing. And talking about, I mean, you have that group here, right? I don't know how many use that here. If you use it, great. I encourage you to do that and exchange information, ask questions there. And if it's hard, just ping me and I will try to add. But usually students know more than me anyway, most of the time, because they're immersed in the subject. Everything I'm like asked, they're wondering about, they're asking me, and they know. Now, today, does anybody have any questions about the problems I presented or the homework problems at all? Yeah?
When you're solving for the pattern solid angle, are the integrals always for phi 0 to 3 pi and for theta 0 to pi?
Yeah, let me, well, a pattern solid angle we have to define. I didn't actually define that, and I don't really worry about it. The solid angle, I think it's on page 431. And let me mention a few things about this. All right, so when you deal with antenna patterns, you're dealing with radiation going out spherically. You with me on this class? So if we're in spherical coordinates for now, and we have a little antenna down here, and we're coming out a distance r, this one's about dead. And call this the z-axis. It won't matter what we call it. We have an angle theta with respect to the z-axis, and if we take the component of this by here, if we look at this as the x-axis, this would be phi. It's the projection of this radius vector r onto the xy plane. I'm trying to draw this and I'm not doing a very good job. If y'all follow me, that's phi, that's theta. Agreed, everyone? Now, when we talked about solid angle, and the reason we do this, well, if I'm out here, if I got an antenna here, radiated power is going in this direction at that point. If I come over here, if I just theoretically come up here, the radiated power is going in this direction. Up here, if I come over here, the radiated power is going in that direction. The point I'm making is the direction the power radiated is going is the radial direction, but they're in different vector directions. Y'all follow me on that? Even though they're all radially away, this r is not parallel to that r, is not parallel to that vector direction. Y'all with me on that? So one way we manage the discussion when we talk about a figure of merit related to antenna gain and things like this, we talk about the maximum directivity, and we talk about the solid angle now, and I'm going to get to, and related to the actual normalized power factor. Let me take you through the whole 9 yards of this, okay? Suppose I had a average power density as a function of distance and all that. So it's going to be some P naught over r squared. It's always the power always falls off as 1 over r squared if it's radiated. Are you with me? I'm just showing you this. It's going to be a function of both theta and phi, possibly. Doesn't have to be. Let me shut that screen off. All right. That's the way it's going to be. Now, this is going to be average power. Flows out radially, can be a function of theta and phi. Now, from this, right here, and by the way, that would be equal to 1/2 the actual electric field strength at a point far away, whatever that is. Call it E of R squared divided by eta naught. And it would be in the AR direction, really a rho, the rho would be a radial direction away, or in the direction of propagation. It's 1/2 magnitude of E squared over eta naught. Everybody with me on this, class? It's equal to that. We're going to leave it at that for now. But when I do this, the first thing I want to do, according to what we're spoken when I was talking about, find the normalized power as a function of theta and phi. Well, when it says normalized power, what that is the actual power up here, right? That would be this one, divided by the maximum value of that. That's just what happens. You find out what the power density is at a given radial range, and then you change R, theta, you hold R constant, change theta and phi, and find out where's the maximum. That maximum value you divide in to the average power. Now what that does is give us a normalized value that has a peak value of 1. Do y'all follow me on that? Now what that actually means is P0 R squared get canceled, and you're left with this. F of theta phi over F maximum, whatever the max value is, of theta and phi. You can forget about P0 and R squared. All that stuff disintegrates. You with me? It's just a function of the angular variation. It's just the peak value of that angular variation. Okay? Y'all with me on this? And I'll give you a concrete example. I'm getting to you. Once I have this, the next thing I do is calculate something called the solid angle, because the maximum gain calculus is really directivity, because we're assuming efficient directivity and gain are interchangeable. The maximum directivity is found by taking 4 pi over the solid angle. I'll just call it omega. And what omega is the integral. It's a double integral of the normalized power density times what's called the solid angle, or differential solid angle. Sine theta, d theta, d phi. Here, theta will go from 0 to pi radians, and phi will go from 0 to 2 pi. I'm going to talk about this in a second, but this is called the solid angle. And let me first, I don't want you to write this down, I want you to listen. I'm about to say, because it's going to be important. You will at least appreciate why we do it that way with a solid angle. If you think about something that has a distance r away, and then you take a look at the differential surface, boy, that's not good, but the ds in spherical coordinates of a surface where I hold r constant, it's called a White arm, and just move it a differential like this and this. That differential surface in spherical coordinates would be equal to r squared times sine theta d theta d phi. How many remember that? That's how you get the differentials. What you actually do is you find the differential movement with a wiggle this way in the phi direction, and that distance would be r, right, times the sine of theta, because what you have to do is get the projection down here, and then move it times d phi, because the arc length is always r d phi, isn't it, class? So it'd be r sine theta d phi this way, and then vertically, it's just r d theta. So that's how you get that. That's using the White arm approach and taking a differential wiggle in phi, differential wiggle in theta. That's how you get that surface. It's a differential surface. Now, when we talk about solid angle, the reason we get rid of r squared is because when you do this calculation of average power here and peak average power, both fall off as 1 over r squared, no cancel. You follow me on that, class? So they just drop the whole thing. I tell kids, most of the time when I'm teaching, just set r equal to 1. That's all you have to do in your mind, all right? Let r equal 1 so it never appears. Now, and the reason you use normalized power is because when you go through this actual calculation where d itself is going to be the maximum power density at a given range versus angle over the average power density, it'll come out to be this. I was trying to allude to that last time, if you remember, right? So to your question, the solid angle is this. It's always integrated over all spherical space. Now, if you think about this, if you did it in degrees, well, from the z-axis, you might say from the north to south pole, it's 180 degrees swath this way, right? And then when you go all the way around from that, from say the y-axis all the way back around, it's 360. So in degrees, it would be 180 times 360. That would be squared degrees. We don't deal with that. We deal with radians. So with radians, all right, if you integrate that differential surface there until r equal 1 from 0 to 2 pi, and from theta goes from 0 to pi, and phi from 0 to 2 pi, you get exactly 4 pi square radians. Are you with me? That's what we'll come down to. You don't need to worry about that, but that's the surface area of a sphere in radians. It's called sterradians, actually. But you might have heard that. How many have heard sterradians before? If you do anything with geophysical work, you're going to hear that all the time. So that's what the solid angle is. It's really it's a intermediate calculation we do to get this. Now I want to say one thing about the solid angle that's important. The smaller the solid angle, the greater the Dmax. With me? So when this thing becomes very small, it means gain is very high. All right? And what it really means is power is concentrated. I'm going to show you a few formulas, approximate formulas that aren't in the book you'll appreciate. All right, so that's Dmax for, yeah.
I was going to ask the next question, but you can
go ahead.
Point. It was about beam width.
All right, we're about to get there. We're about to get there. So anyway, that's Dmax. Now let me just, yeah.
For solid angle, for like 8.5, if they state that like phi is 0 to pi, would you change your?
Yeah, because here's what happens. What happens if this is zero? Suppose from 0 to pi over 2 it's 1, but from pi over 2 to pi it's 0, right? Well, then your integral of a non-zero value is from 0 to pi, isn't it? And you wouldn't integrate the rest of the way because you're integrating 0 in d phi or d theta, and 0 integrated over anything is still 0, isn't it? That's the reason. The limits still exist, but the fact is this thing will change values. So when this thing inside here is 0, you don't worry about it. Agreed? All right, now back to your thing. That's the maximum directivity, but it doesn't give me the angular function. And here's what I want you to take from this. Now get this. Once you have the maximum directivity, the actual directivity, d is a function of angle, theta, and phi, is just the maximum directivity times the normalized power density as a function of theta and phi. So you just take the maximum directivity, multiply it by the normalized power, and now you have the directivity as a function of angle. You got that? That's real important. You need the maximum to do this, though. And that's where this calculation happens right there. Okay? Everybody go there? I'm going to get to some of the problems, but I got to make sure I take you through this. Now, a natural question is, well, what about beam width that they mentioned? That's my next topic. And I hope you appreciate some of the reason I give you homework is to also cause you to think. You can read in a book, but you're going to have natural questions that I can address in class. And the best way to learn is come to class with an expectation of answers. This is a question, I don't understand this, ask it, and probably a lot of people will be, they'll understand. And when you have that, when you beg for that thing, it really sticks with you too. So next we do beam width. Well, I'll say one other thing. On the internet, there is so much information about things that I'm talking about. If you go there, you might be overwhelmed because there are things that there are terminologies and things that aren't consistent with Dr. Wentworth's book. So I'm just warning you, if you ever feel that way, don't worry about it. Just stick to the way I'm teaching you, because a lot of times people are going to use approximate formulas. They're going to use all sorts of what a technician would use to get answers, not what an engineer uses. So beware of that. So now we talk about beam width. what is beam width? Well, the width of a beam. What kind of a beam? We always talk about the power beam width, and here's what I mean by this. If this is the magnitude of the power density, and I'm going to use normalized. It doesn't matter if it's normalized or not, but I like normalized. And I'm going to do this. I'm going to say phi is held constant, pi/2 radians, and now I'm graphing that. And so I'm going to graph it versus theta. So what I'm really doing is saying that if I have an antenna like this, and this is the z-axis, what I'm actually going to show you is an antenna pattern like this, where it's going to have a maximum here, in this direction. It'll be broadside, perpendicular to the length of the antenna. And I'm even going to say that this actually has a normalized power pattern of the sine squared of theta at this phi value. Now don't worry about that. That really doesn't matter what phi value. It's the same in all phi values. And this is a real antenna. It's called short dipole. So what does it look like? Well, if it's sine squared of theta, what is sine of 0 when theta is 0 when you're looking straight up, class? Well, what's sine of pi/2? Isn't that 1? Sine of 0 is 0, isn't it, class? Right? So you start at 0. What does that mean? When I'm looking straight up, I have a radius vector of 0, so I'm here. Now, add 45 degrees to that. What's the sine of 45 degrees or pi/4? Anyway. Well, isn't it 1 over square root of 2? Right? So square that, it's 1/2, isn't it, class? So now come out here. Here's 45 degrees. I come out and I show a radius vector that this would be 1/2. You got me on this? Now plot another point. Go out to 90 degrees. What's the sine of 90 or pi/2? Anyway. There's no wrong answer. 1, right? 90 is 1, right? Sine squared would be 1. That's out here. Call it here. Tell you what. I'm going to do it spherically this way. And then I'll do it with linear. So if I was to take a look at this, this would have this configuration for the pattern. That would be the normalized power pattern. Here it would be 1. And I'm graphing this. I was going to graph it linear, but I'm going to graph it spherical so you see it better. Does that make sense to everybody? Now, when they talk about beam width, again, that's a figure of merit. So when I use that term figure of merit, when you're an antenna, always think of how good something is. Like a 5-star recruit coming to play for Auburn is a really good recruit, all right? Think of this, think of like gain as that kind of figure of merit, all right? That's the way I think about it. It'll help you get a handle on it. We talk about beam width. The narrower the beam width, the better usually for gain. Remember that. So what is beam width? Well, beam width can be either between nulls or peaks. The beam width we use is the half power beam. I'll explain it. Half power beam width is this in a nutshell. You find the point where the normalized power is 1/2 its peak value. If it's normalized, the peak value is 1 by definition, isn't it? Now pay attention to this part because it's good. So at a half, wouldn't that be 50% of the maximum? So you draw a line straight up. Where did that occur? That occurred at 45 degrees or pi/4, correct? Now if it's a sine squared pattern, then this is the trace out. Where does it go down again? Right here, right? It would be 1/2, and what would the angle be? Well, the angle between here and here would be 45 degrees, wouldn't it? It would be symmetric, wouldn't it, class? That's 135 degrees, isn't it? So from here to here, it's 135 degrees, and the beam width is actually the distance from the half power point through the main beam to the other half power point. Now in this case, it would be what? 45 minus 135. For an easier calculation, we just take 180 degrees and subtract 45 and 45, or 90, It'd be 90 degrees. Do you follow me? So the distance between here and here would be the half power beam width. And in this case, it would be 90 degrees. And that's lousy. Just telling you. Okay? Can you all see this, class? Now, I'm going to draw something on here again because it'll help you see what I'm doing. A high gain antenna, typical beam width is 2 or 3 degrees. But I want to draw this out here and explain as I thought. How many are with me so far? What I'm doing? You good with this and far back too, guys? All right, now just listen to me. I'm going to erase this for a reason. I'm going to stick here. Now if I take this, here's my antenna, but now it's going to be a high gain. This is going to be a high gain or high directivity antenna. All right. And here's typically what it'll look like. It'll be something like this, where this, between the half power point, this angle here will be, they'll call this theta, and it'll be beam width, and you can put half power if you want, but it's almost always implied half power. That beam width may be only 3 degrees, 3 to 4 degrees. Now that's called the main lobe of the antenna. Do y'all hear it? I'm going to write it down. This is called the main lobe. Now that's not the only story. The higher the gain antenna, unfortunately, with a few exceptions, you also have something spring up called side lobes. And then you're going to get this kind of phenomena. These are side lobes. Remember, what this really is doing is showing you how the power is arranged or how it's propagating from an antenna. Are you with me on this, class? So it just tells you the information if you're an engineer about the power radiating. Obviously, if you want to radiate power on target, you're not going to have an antenna like this aim and expect power to go up the antenna. This is another piece of information that it all fits together, but whenever you have a straight wire antenna, no power is ever launched along the axis of the antenna, this way or this way for a straight wire antenna. With me? All of it is going out at some angle other than 0 or 180 degrees. Okay, class? Y'all with me? So if an antenna is like this, nothing's radiating that way or that way. It's radiating that way. Okay? That's important that you follow me on this. Now, these side lobes, in general, have amplitudes that are much less than the main lobe. You can't get away from them. They spring up. The more gain you get, or the smaller the beam width in the main beam, the more these little guys pop up. They're just unavoidable. You all follow me? And there's all sorts of tricks to minimize this, because that's a waste of power if you really want to propagate that way. You all follow me in that, class? If you're trying to get energy, if you're putting a radar on a target, you want to pour as much power as you can down the main beam, because then when it bounces back, you'll know that's where the target is, in that direction. If you got a real big wide beam, you'll launch a signal and get something back. You don't know if it's out that way or that way. That's the reason you want a real narrow beam. You follow me? Also for communication purposes, especially in deep space. Now, space is starting to get back in vogue like it was in 69, 70, and deep space probes are coming out. I don't know if it's true. Years and years and years ago, the Japanese came up with a plan to mine asteroids for precious metals and rare earth elements, because asteroids are loaded with things. Besides gold, they have tungsten, titanium, things for the aircraft industry. They have all these things. Problem is how to get there and how to get back. So now there's a whole new branch, a lot more interest, because we have things called rail guns and other things that can launch things in orbit without the actual weight of rocket fuel. It's about 90% of the weight from the launch vehicle is burned up in fuel. With a railgun, they can toss it way up there and toss it in low Earth orbit. So it's becoming cost effective to do some of this stuff. I don't know if it'll ever happen. But when you're doing that and you got something out there, a couple million miles, the last thing you want is a wide beam. You want the thing to be as narrow as possible. Did anybody ever see the movie Contact? I used to be able to talk. There's a picture in there of this gigantic antenna array of parabolic dish antennas. Now you all know when you take a look at your dish antenna on your roof, you all seen these, right? Those are high gain. They're about 30 to 50 dB, right? That's of the order of 1,000 to 10, 20,000 gain linear. That's a lot. But they have an array. Now gain, all right, the gain of an array is the gain of one element times the number of elements. So if you have n squared n elements, your gain goes up by that being an element. I mean, I'll spend more time on that later, but what it amounts to is they'll have a large array of parabolic dishes for deep space work for one reason. Then they get a super narrow beam, and they don't lose much power for transmitting as well as receiving. You follow me on it? How many heard of astrophysics, right? Or astronomy? Well, that's the kind of stuff these guys use with radio telescopes when they're going way deep into space and they're looking or listening. That's what they use, that kind of gauge. Anyway, they have super narrow main lobes and very small side lobes. Now, here's an approximate formula you write down. It's not in your book. And I'll put it right here. Is that clock right?
It's 12:30 right now, yes.
Okay. So, if you talk about gain in general being the efficiency of an antenna times directivity, and we assume efficiency is about 1 or 100% efficient, then gain is about equal to directivity, and we can say both gain and directivity are approximately equal to 4 pi divided by the beam width, and this is half power beam width, in the phi direction times the beam width in the theta direction. Remember, these are half power beam widths right here. That's an approximate formula. That's very useful. Now before, what was the gain of directivity? It was equal to 4 pi, right? Over the integral, double integral of the normalized power as a function of theta and phi times the sine of theta times d theta d phi. And this goes from 0 to pi to 0 to 2 pi, right? That's the actual formula. This is the approximation. Now here's why. Because this guy right here, the beam width, if it's big, again, if they're small, this is for something where you have theta beam width, phi beam width, small. So a good question to ask is how small? Oh, one other thing. These have to be in radians. So a good question is how small? Well, in degrees, about 5 degrees or less. Follow me? So what's 5 degrees in radians? Well, if you say beam width less than or equal to 5 degrees, what you're really talking about what? 5 times pi over 180 in radians, aren't you, class? Right? Because radians, if you got degrees, you want radians, you take the degrees, multiply them by pi, and divide by 180, correct? If you look at that, what do you get there about? Well, 5 into 180, right, is what? Well, 10 into 180 would be 1 over 18. 5 into 180 is 1/9, isn't it, class? Y'all agree with that? So this is about pi over 9. Right there.
Wouldn't it be pi over 36?
Let's see. Did I mess that up? Let's see. If you got 10 over 180, I'm sorry, what you were right. Well, wait a second. One over 18.
36.
Yeah, 1 over 30 is pi over 36. My bad. You're absolutely right. pi over 36 would be, and that's a small angle, by the way. I don't even know the number on that, because pi is about 3.14. Yeah.
What's the difference between the 5 beam width and the theta?
Remember, theta is the beam width from the z-axis, right, from the z-axis downward, and phi would be this direction. For
That's the
instance,
theta?
this would be theta if this was z, right? Phi would be in the horizontal plane. Now, actually, what a beam looks like is this. It would have a lobe this way, right, but there would actually be a lobe this way, too, if you can imagine that. It's like think of it as a teardrop falling, just turning on its edge. All right, so there's a width in both phi and theta. Most of the time for narrow beam, and for focused beam antennas, they're about the same. But there are areas, like if you want a very narrow beam this way, then you want a big old chunk of parabolic this way. And if you want fairly wide this way, it'll be narrow. The wider, you all seen rotating parabolic dishes? Like, they look sort of like this, and they rotate. Y'all see it? Well, the wider this section is, the narrower the beam in that plane. So as it's rotating, the width of this has to do with the beam width there, and the width of this has to do with the beam width here. And usually for navigational radars, they want real narrow beam width this way, but real broad this way, because usually for ships on the sea, they don't care about whether the ships, they know the ships, if they're looking there or there. What they care about is where it is in azimuth. That's what they want to know. So that's theta and phi. I'm glad you asked that, because I didn't explain that. You good with that? Now let me give you a concrete example of some of the things I'm saying. So I gave you problems with solutions, all sorts. One of the things is I asked for like the directivity, right? Based on some things. And I also asked, I think, for the beam width and things like that, right? So let's take the classic example. If we have a pattern, a normalized power pattern, of just sine squared of theta. We were talking about that before, right? If you take a look at that, the beam width, remember I showed you how to calculate we already determined the beam width was 90 degrees, didn't we, class? That's in theta. In phi, there is no real meaning to beam width because it's the same in every direction. It doesn't vary. What this actually looks like is, if you were looking at it, would be this. You would have, I call it a donut. You could swing that thing around the z-axis and it looks the same every which way. Do you all follow me? So the beam itself is not a function of theta, of phi, it's a function of theta only. And that's it. That would be for an antenna that's in the z direction. Okay with that? Yeah.
It's because it's like a donut?
Well, if you think
It goes
about
all
a
the way
wire
around.
antenna, right?
Yeah.
The maximum power is perpendicular out, right? That way for a short dipole. All right, when you look straight up, what happens? Nothing, right? But would it matter if I'm looking that way, or that way, or that? The wire looks the same in every case, right? And that's why there is no beam width. It loses meaning in the phi direction. It doesn't have one. It's the same in every direction. You good with that, everyone? All right, back to this thing. Here we saw the beam width, 3dB beam width, usually it's called, was equal to 90 degrees, 45 times 2, right? Now there's a thing called the beam width null to null, and that's like, what's the beam width from the absolute null to the absolute null? It's never really used. I mean, it may be used in a problem, but it's not really used in the real world. It's half power beams that they always worry about. Just telling you the facts about it. So that's the beam width. Well, what's the directivity if that's normalized power? How would you get that? Well, what's the formula? The maximum directivity would be what? 4 pi, right? Then I put down the double integral of what? Of the normalized power, right? So it's sine squared times the solid angle, which is sine of theta d phi. Theta would go from 0 to pi. Phi would go from 0 to 2 pi. You all remember that? All right, what's that? How would you do that integration? In this day and age, you have symbolic calculators, so you would say, I would use my symbolic calculator. Correct. I'm not stupid. Well, back in the day, when you actually had to do this stuff, what would you do with this integral normally? Anybody remember?
Would you split it up and then multiply them together at the end?
What you'd actually do is take sine squared and make it 1 minus cosine squared, wouldn't you? Isn't that what sine squared is? Now, then you would make what? Yeah, you would say, if I let u equal to sine theta, then du would be what? Or you could let it be cosine, would be equal to cosine theta d theta, correct? Right? And you look in here, what do you have? Well, I have sine theta, and this is actually, you would have a sine theta times 1, and that's a straightforward integral, that's just cosine theta. Then you would have a u squared du integral here, correct? And you would do it. When you do this whole 9 yards on this one, you end up with this thing, whole thing being equal to 8/3 pi. Did anybody do this? This whole thing I just circled is 8/3 pi. You can check me out on here. And D max for that antenna would be 1/2. I mean, sorry, 3/2. I'll just tell you how it goes. You do this integral, I have 1 sine theta, right? Integrate sine theta, you get what? Minus cosine theta, correct? Minus cosine theta, evaluated at pi is -1, minus the minus is +1. At 0, it's 1, right? What it'll amount to is the first part of this integral will be 2. Second part, I have u squared du, which would be u cubed over 3, correct? You evaluate that, and you're going to get 2/3. When you do the math on this, it'll come out to that. And I'm trying to be aware of time, because I know you got a quiz. Are you with me on what I'm saying here? That's a straightforward integration. You have symbolic calculators. This is no challenge to you, all right? If you had to do a longhand, you use substitution, what I showed you, it works. So for this would be D max would be that. Now, I want to cover one last thing before the quiz. We did this last time. I want to make sure everybody's on the same page as me. Remember, I started off by saying, let's gain use for focus, right? So if we have an antenna, and I've got a power, P transmitted there, and I got something I give an R range away, and I want the power density out here, the average power density. How did I get that? Let's assume I know the gain of the antenna or the directivity. So I know what this is. What do you always start with? Assume that there's no gain. It's isotropic, right? Take the total power over 4 pi r squared. That's the amount of power that would be launched, that would go through a spherical surface at a given range if there was no focusing. Are you with me? It's just out there, and it's equal in every direction, right? So it's total power over 4 pi r squared. But what does gain do? It sharpens it. So that would be the power density in watts per meter squared. Follow me? How many are with me? Now listen carefully, right? All right, not done. Now how do I get the electric field strength from that? Suppose I got that. How do I get the magnitude of the electric field strength that far away? Tyler?
Square root 2 times.
Well, you're going further than I needed. The equation would be 1/2 the magnitude of E squared over eta. And eta would be really eta naught if it was there, or 120 pi. Y'all agree? How many do? Gotta make sure. You guys, you got it for me? All right. Yes? Oh, you got it. All right. Last question. Not you guys. Somebody back here. How do I get the H field? Got the E field. It's propagating wave. Not you guys. Say it again, Bob.
E over eta naught.
We know E over H is eta naught, right? So if I wanted H, I take E over eta naught. You're right. Y'all hear her? Okay, take everything off your desk.